So let's spend some time talking about research. In particular, I want to share some research that I've been dabbling in that I think has a lot of really interesting opportunities that you might be interested in pursuing, having to do with how do students interact with visuals. When I say visuals, we're talking about how do they interact with movies, how do they interact with graphs, how do they interact with outline forms of any of this sort of stuff. How do people do this? How do students learn from visualizations? And if I click this over here, okay. So the core thing that what we do here in the science education program is we're trying to figure out just how is it that we best teach students? Some of us are teaching physics, some of us are teaching astronomy, some people are teaching teachers, other people are teaching professors. It's a wide variety of things that we do in terms of who we're trying to teach. And the real question we're focused on is how do we best teach learners? Now, most of the structure that we do this under is we do this under a virtual collaborative of researchers called the CAPER team. And some of you are very familiar with CAPER team. CAPER is an acronym. It stands for the Center for Astronomy and Physics Education Research. It is not affiliated with the University of Wyoming. It is an independent entity of researchers literally from all around the world that work under this banner on worldwide global projects. And we can spend some time talking about exactly how that infrastructure works. But the real goal of CAPER is to figure out what we hope you think we might believe that we know about how it is that we teach students. And sometimes we're better at it than other times. But there's essentially two ways that we go after doing this. One is we spend a lot of time looking at the literature of teaching and learning. And we try to say, okay, if this worked really well, this particular teaching strategy worked really well in chemistry, particularly like how do we visualize molecules? How do we apply that when we're teaching physics? Or if we look at the literature about how people study graphs from economics, how can we apply that to the teaching of biology? So part of what we do is we spend a lot of time in the literature looking at what other people have done in other subject areas and try to transfer that between disciplines. Sometimes that discipline switch happens easily. Sometimes it's totally different. For example, in physics, the domain of physics, some of us are teaching the calculus-based physics course to students that are someday going to go on to become engineers. And some of us are teaching the college algebra-based physics class. Those students may go on to become architects or doctors. What works in one setting may or may not work with other settings. In fact, physics tends to be a subject that's very dependent upon who the learners are. The other thing we try to do, besides looking at the literature from one subject and begin to apply it to other subjects, is we try to come up with answers based on experiments. And you can imagine what those experiments are like. We take a group of students in the 8 o'clock class and we do this to them, take a group of students in the 9 o'clock class and we do that to them, and we compare how they might be different. Now, sometimes people talk about this in terms of it being the difference between theory and practice. And some of you know my philosophy that I've picked up from Mike Bennett, who picked it up from Yogi Berra, about what is the difference between theory and practice. Well, the difference is, in theory, there's no difference between theory and practice. But in practice, there is a big difference. And that's really kind of where our research is going. Let me try to give you a better example. So here's an image from my astronomy book about the phases of the moon. Now, give you a second to study this image. It's not unique to my book. Most astronomy books have this image. Many high school physics books have this image. Many middle school, junior high school, earth science books have this image. And this is a pretty complicated image. Turns out if you know how moon phases works, this is a great image. Everything you need to know is here. But if you don't know how moon phases work, well, this is a bit complicated. I mean, there's 8 different moons, and some of them have craters, and some of them don't. Sometimes you have a moon like at position C, where the right-hand side is bright, and the moon right next to it, the first quarter moon, its right-hand side is bright. But if you look at the bottom of the image on at position F, you've got the right-hand side of the moon is bright, but the waning gibbous moon beneath it, the left-hand side of the moon is bright, which can be confusing. There's a lot of stuff going on here, and in fact, I would argue that this is a terrible, terrible diagram for learning about astronomy, unless you already know how phases work. Now, there are other things that we tend to do, and I'm going to show a short video here. Here's another video that somebody might use about phases of the moon. This is actual, authentic, real scientific data about how the moon changes shape over the course of a month. In this particular image, they show the names of the major geologic features, like craters. The top left-hand corner, you can see where the moon is its orbit around the Earth, holding the Earth constant. You might also notice the moon kind of swings back and forth. This is called a libration. Turns out the moon we don't always see exactly the same side of the moon. The moon wobbles a bit, and as it wobbles, we're able to see all kinds of different spots on the moon. So you can ask the question, which is a better way to teach moon phases? Is it this image this way, or is it the movie we looked at? And you can already imagine the experiment, right? The experiment is you take one group of students and you teach them moon phases showing them this graphic. You take another group of students and you show them show them using that video, and you can compare the difference. You can also do this whether we're talking about being in a museum environment. How do students learn sitting in a planetarium versus how do students learn sitting in a regular classroom? And we can ask these sorts of comparative questions. The real question that we're trying to focus on here that I want to talk about tonight with you guys is this notion of, we've all heard the phrase, a picture's worth 1,000 words. And I think that's probably true. What that means is often you can look at a picture and it takes more than 1,000 words to describe what's there. But one question I ask is, if you alter the picture a little bit, can you make it worth 10,000 words? Can you make it worth 100,000 words? Just what can you do to an image to make it have even more and more information? For example, suppose we take that picture of the moon and we add arrows and we add text boxes. Does that help? Or what if we add the words that I'm saying to you? What if we add those at the bottom of the screen, like closed captioning you might see on a television? Or when I show you a picture, should I shut up and just stop talking? Can you learn more by looking at that picture of the moon phases by me not trying to explain it and you just trying to figure it out? Well, these are all the kinds of educational experiments that any of you might be interested in working on, that many people around the world are working on. And particularly in astronomy, this is something we want to know a lot about. So probably the world's best expert on multimedia learning is not an astronomer. He's not even a science educator. He's an experimental psychologist, and his name is Rich Meyer. And if you haven't read much of Rich Meyer's work, you will. He's very ubiquitous. He's very prolific. He's written a lot of stuff. So a lot of the work I'm going to be telling you about today here comes from his work. This isn't my research work, but work that he's been working on. Now, I need to give you sort of the theoretical framework for what we're talking about. And some of you are cringing because some of your professors will talk about theoretical framework and you go, what is that all about? So anytime someone says the word theoretical framework to me, what I imagine in my head is a sandbox. Like you might use it out in the backyard to either cats use for one reason or you use to build stuff in. That's got four sides to it. And it's these four sides that work together to constrain the research questions you might ask. So, for example, if we're talking about visualizations and how you might teach science better, one side of the sandbox that kind of ropes us in and guides our research has to do with, well, what is it that we want students to know as a result of looking at these moon phase diagrams? Is it we want them to know the names of the moon phases? Or is it we want them to know how moon phases work and be able to predict when the moon's going to be in a particular place? Or do we want them to be able to transfer this and say, suppose you're on the planet Mars and you're looking at its moons, how would you predict what the moons are going to be doing on the planet Mars? In other words, what is it that we want students to learn? Matters. The second thing has to do with how are we doing this study? Are we doing this study by doing comparisons, by doing experiments? You take your 8 o'clock class and do one thing with them. You take your 9 o'clock class and do something else with them. Or are we just looking at the literature and saying a priori, the research says this particular approach should work best, and does that shape our experiments? All right, what about the third side? For the third side of the theoretical framework has to do with the assumptions. And in every research project you read about, every research project you do for a class, there are always particular assumptions. And the assumptions that we're going to make here, the things we're talking about, is first of all, that when your brain receives information, that pictures go in one side of your brain and words go in a different part of your brain. And those two things don't mix. That's the first assumption we're making. The second assumption we're making is that you can't absorb all the information that's being thrown at you in one particular semester or in one particular class or even one particular lecture. And the third assumption is that if you're going to understand this stuff, you actually have to actively pay attention. You can't sit there and just kind of listen. You have to be actively processing the information in your brain and comparing it to what you already know versus things that you don't know. What's new information? What's contradictory information? And finally, the fourth part of the theoretical framework, what we're talking about here, has to do with how do you as a human being manage all the demands that your brain has to deal with. When you look at that picture of the moon or moon phases, you watch that video of moon phases, what's extraneous? For example, are you sitting in a hot room or a cold room? Are you looking at this on a tiny little iPad screen or your giant screen in your office? That's extraneous information, but it's also important. There's also essential processing. In other words, do you know the names and what we're talking about? When I say the moon and moon phases, do you know what that means? And then finally, you also have to manage what we call generative processing. Generative processing is when you begin to make connections between what you're learning about versus what you already know, your prior knowledge. And some of you may have a lot of prior knowledge about moon phases. Some of you may not have any at all. So when we talk about theoretical frameworks, and all semester long we're going to spend a lot of time talking about theoretical frameworks, I want you to imagine what are the walls that constrain the topic that we're talking about. And I usually think of it as a sandbox. All right, let's do an example here. So as we talked about last week, I spent some time in Hawaii working in some of these ancient temples trying to figure out their alignments. Now, here is an image of an alignment that's probably more familiar to you from Stonehenge. This is in England. It's 500 or 600 years old at this point. And there's an image here that describes the stones that are located in the center, the positions of where stones would be located at the outside. It shows you the sunset positions, the sunrise positions at different times of the year. It shows you the heel stones, the chalk banks, the Aubrey holes, as well as has a description, a caption that explains what this is all about. The question is this a good image or not? Turns out you can do this experiment and say, do you need to give students a simple image or a complex image, and in which case do they learn more? You probably wouldn't be surprised that when you do this, ask this experimental question time and time again, the more information that's given in an image, the less students learn from it. We find that when there's a lot of extraneous words, extraneous pictures, these things all get in the way of students beginning to manage. Now, I need to be careful here and give you a caveat. When we talk about students learning things, I want to be clear, we're talking about the average student. And as science education professionals, many of us work in universities or in museums, we often begin to think of, well, what does it mean to me? What's easiest for me to learn? And it turns out that you are not the typical client. You're very unusual. You spent tons of money and tons of years in graduate school. You spent tons of time thinking about teaching and learning. You're not the average person. The average person is who we're talking about. So sometimes if I say something about, for example, students learn better if with a simple diagram compared to a complex diagram, and you say, oh, no, baloney. I learn better with a complex diagram. Well, you might learn better with a complex diagram, but you are not the people that in general that we're talking about. I noticed that Astrid pointed out here in the chat session that she was able to go to Stonehenge a couple of years ago and got to be there at sunrise. Oh my gosh, with a very limited group of people. That would have been fantastic. But I loved that. All right. So let me show you. Oh, no, I won't do that. I want to do this here. No. There. Here's another image that we might show students. This is Tycho Brahe. Tycho Brahe was a very famous astronomer who lived back in the 15 and 1600s, was probably perhaps the best naked eye astronomer ever. He was able to make very, very accurate measurements, the positions of the stars and planets, much better than anyone had ever done before. And he was very, very patient. He was extremely wealthy. He was a Danish nobleman. You might notice his picture looks a little weird, and that's because there's a very famous story about how he'd lost his nose in a duel over a woman. He had met this woman. He was challenged to a duel and against an expert swordsman. The expert swordsman did not kill Tycho Brahe, fortunately for all of us astronomers. However, he left him permanently disfigured by ruining his nose, and Tycho Brahe, being a wealthy man, had a wooden nose as well as a gold nose that he would wear. He wore the gold nose to fancy occasions. He also is very famous for the way that he died. He died of bladder failure because there was an event where he was at the king's palace for a ritual dinner, and in those days when you went to dinner at the king's house, you didn't get to go up and go to the restroom whenever you needed to. You had to wait until the king had left to go to the restroom. And they were sitting up late and they were drinking and having a great time, and the king didn't ever bother to get up to go to the restroom. And as it turned out, this bladder infection resulting from this killed Tycho Brahe. Now, my question for you is, what is it that students are going to remember most about Tycho Brahe? Go ahead and type it in the chat there. Given the story I've just told you, what is it that students are going to remember? Cody says his bladder. Astrid says his nose was cut off. There's more noses, more bladder infections. Now, is that the thing that I, as an astronomy instructor, want you to know? The answer is no, it's not. What I want you to know is that he was a great observer, a very accurate, a very patient, very meticulous observer. Turns out, we often try to tell students interesting stories about the scientists we're studying. But students can only pay attention to so much, and they end up paying attention to what the interesting parts of the story rather than the things we want to remember them. And so we call this the coherence principle. And it's the idea that if you really want students to know a particular thing about individuals or particular things about a physical system, having extra things in the picture, extra pieces about the story that we think are interesting and make this science more human, in fact, gets in the way of students learning. So that's another example of this. Humor is another place. The number of people that have tried to look at and study the impact of using cartoons or using humor in a planetarium or in a classroom has been a lot. And universally what we find is the more times we use humor in a classroom, the more times it turns out the students learn less and less. And this is because students can only process so much information, and they pay attention to the humor rather than paying attention to the ideas you're trying to get across. And again, you can try this experiment with your own students. You take your first hour class and you fill your class full of cartoons, your second hour class and you don't use any cartoons. You measure the difference in what they've learned, and what we find out is that humor universally makes students learn less. They might have a better time, they might like you better, you might get better end of class evaluations, but turns out when we use humor, we actually negatively impact students' learning. And again, the number of papers that have reproduced this is a lot. And I've listed a bunch of them here. I don't expect you to know those. If you want, I'll make a copy of this. All right, there's one example. The giving students too much information, whether we think it's interesting, whether we think it's funny, or whether we think we're just being complete and rigorous, oftentimes means that our students learn less. A second idea is what's called the signaling principle. Turns out when you give students an image, like this image from a textbook about global warming, as it turns out that when there's a lot of information, we can increase the amount that students are able to retain by highlighting particular amounts of information. So we can do the experimental test. We can show half the students the color picture on the left and half the students the color picture on the right, and then ask them questions about the image. Turns out universally students do better looking at the right-hand image than they do the left-hand image. By the way, I made the right-hand image. All I did was make a copy of the left-hand image, and then I used the color correction and turned it into a grayscale image. Then I made a third copy of the color image and cropped it down just to show the part I wanted people to pay attention to, and then pasted it over the top of the grayscale image. It took about a minute and a half to make this image. And we know that having images like this helps students learn more. And again, there's a bunch of papers that describe this, which you can read at your own leisure. One of the things that we often argue about in our house has what we do with what we call the redundancy principle. The argument in our house goes like this. We're watching a TV show as a family, and some of the people in our house want to be sure that we have the closed caption session on. And other people in my class, in the house, do not want closed caption. Now, if you don't know what I'm talking about with closed caption, I'm going to try to show a video here, and I'm going to assume it's going to work. This is a clip taken from Warehouse 13. All right, so I'm going to pause it there. And we can ask the question, does having the closed captions on help students learn? As it turns out, it does not help students learn to have the closed caption on there. You might say, wait, why are there students that are hard of hearing in my class? Well, what about students that are deaf and can't hear the audio? Well, those are exceptions to the general rule. The general rule is if you show a video clip with a narration and without, students that do not have the narration learn more. Now, this is of great frustration to me because in my house, I'm always arguing to have the closed caption on the television, and my kids are arguing to have it off. I think that may be because I'm hard of hearing, but what happens in my house and what happens in the classroom are probably two very different things. All right, so let's move on here. Again, a bunch of research that I can point you to that talks about this. What about having to do with when images are shown? Oh, no, I want to do that one. What about when you have complex images, particularly in a textbook or maybe in a handout that you're using or in a PowerPoint, where you've got different parts of an image? In this particular one, we were looking at the formation of a black hole, and you've got panel A, panel B, panel C, panel D, and a nice detailed caption underneath. Does it matter where the caption is placed? Again, we can do that research. You can imagine what the research project looks like. You give half your students this image with the caption underneath, and you give the other half of the students the image with the captions set aside in balloons, just like you might see in a comic book. You may or may not be surprised to learn that students learn best when the information is presented next to the image. And the reason that is, I think, because when you have this situation where the caption is below or different places, students don't really take the time to say, okay, here's word A. Now let me go up and find the image of A. Now let me go back down and read B, and let me go find the image of B. I don't think students go make that transfer back and forth so much. So it turns out this sort of format where you have the important words next to the important parts of the picture, like a comic book, impacts student learning. And again, there's a bunch of references citing this. None of this work has been done in astronomy. No one's ever done this experiment comparing A to B. Now that would be a really good study for some of you to work on, particularly those of you that are here talking about some of your research classes. All right, so the stuff that we've been talking about to this point is really all about managing all of the extra information that distracts people away from the core. Coherence, signaling, redundancy, continuity, contiguity. Thank you. That's right. But let's talk about things that have to do specifically with essential ideas, things where you're really trying to get to the core of the information. Well, let's go back to this. So one way to present information to students that we know is better than putting the caption off to the side is putting the information right next to the pictures. How does that compare to presenting all four pieces of information at the same time versus presenting one piece of information and then the second piece of information and then the third piece of information and finally the fourth piece of information? Now, what most scientists would say is, oh my gosh, you got to look at it all at once to be able to see and make comparisons. Turns out for most people, that's not true. For most people, they really need to see these things individually because when you show them individually, students score higher. So whether you're showing them individually or whether you're trying to use humor, you can distract what students are trying to learn. As a case in point. See, now you're paying attention to the cartoon instead of paying attention to the coherence idea. All right. One thing we do know is that advanced organizers work. If we can help students understand what it is they're about to learn about and get some of the vocabulary out of the way, it does distract from the discovery and from the surprise, but it's much more efficient for students if they know what they're going to learn about. So for example, suppose you're getting ready to teach a unit on astronomy. Spending just a few minutes to say, you know, we're going to talk about these things called stars. And there's a really close one. It's called the sun. Most stars appear to occur in groups. A big clump of stars we call a galaxy. Now, it turns out there are lots of clumps of fuzzy clouds out in the sky. Sometimes they're galaxies. Sometimes they're just a clump of gas. And these clumps of gas are called nebula. And when we look out in the universe, it turns out that there's gazillions of these clumps of stars called galaxies. And just giving students a kind of warning of all the different kind of words we're going to be using when we go into our astronomy unit seems to work really, really well. And you can do the experiment. If you do the pre-words versus not, we find that students on the pre-words learn better. One way that people often manage this is they have something called a word wall, where they'll have a big piece of section of the classroom where they'll put up all the important words as they come to them. And again, this research shows up again and again in a variety of different settings. So earlier we talked about having a caption next to the picture. What about if you don't use a caption at all? What if you just read to students? You can imagine an experiment that says, I'm going to show students a pretty picture, and I'm going to narrate or just verbally tell them what this picture is about, versus having a group of students that have the picture and have the printed narration next to it. You can do the experiment about which works better. Turns out the students learn more from pictures than they do from words and pictures. Again, it's this idea that a picture is worth 1,000 words. Adding more words to the picture turns out to be distracting. And again, across a wide variety of domains, we've seen this research done. Nobody's done this research in physics. No one's done this research in astronomy. No one's done this research in geology. Really interesting research projects could be going on here. What about if we are having students use words? Suppose we make them impersonal versus personal. So imagine a passage in a text or on a PowerPoint slide, or even one that the professor says that says, hey, you know, when astronomers look at starlight that's been split up by passing through a diffraction grating and split into a spectrum so we can see all of the colors of the rainbow, how does that compare to either a passage that students read in a book or something on a PowerPoint slide or a professor that says, hey, you know, when you look at starlight and we split it up into different components, let me tell you what you can see. Now, this sounds like this is nuanced semantics, right? Does it really matter if we're talking about astronomers, the other, or does it really matter if we're talking about you, the individual? Turns out we can test it, and every time we test it, it turns out that the personalization principle matters. The students learn better when they're talking about them and themselves and what they can see versus what some astronomer somewhere else on the planet can see. The one place where this doesn't apply is in the context of teaching cosmology or in teaching evolution, biological evolution. Turns out because people have so many personal beliefs that they carry around with them, either they've been given to them by their social structure, their culture, their parents, their church, whatever. Often if we say, hey, what do you see when you look at fossils? It gets us in trouble. Turns out in those particular cases, we say, hey, when a paleontologist looks at a fossil, here are the kinds of things that paleontologist might see. Turns out to be much easier for a student to manage than having it talking about them and what they see. But it's only in these highly emotional challenged positions. And this is why things like kinesthetic astronomy that Jana has used so much of, why kinesthetic astronomy works. It's really all about them, and it's very egocentric. And it's not tied to an emotional connection to a societal value. All right, and again, more research for that. One thing we try to do often in science is we want to explain that science is done by a diversity of people, and not just old guys and with beards and white lab coats smoking cigars, but people from all walks of life and from all races, all genders. And so often what we'll do is when we have quotes, we'll put pictures of these individuals there so you can see that that person really is a human being that doesn't look like the traditional view of a scientist. Does that help students learn or not help students learn? As it turns out, if you put the person's picture next to the screen, it doesn't help them anymore. it doesn't really hurt them. It's not really a distraction as much as as some of the other things we've been talking about, but it doesn't help. You might think that by making this statement more human, by putting a person's face to it, they'd be able to embrace it more and learn it more. Turns out, no, doesn't matter. So, for example, in the video that you're looking at right now on your computer screen, my picture is there. Is my picture being here helping you learn the material, or is it being distracting from learning the material? Here's a slide here showing another class. This one was one that Stephanie was teaching about, and some of you were probably in this class. I think it was a Nature of Inquiry class. Jan, I think you were in this one. Does having the instructor's picture right here talking to you, does it help or does it distract? Turns out, statistically, it distracts. You learn less if my picture is sitting here right here talking to you. Now, does that mean I'm going to turn my picture off? Nope. For two reasons. Number one, I'm vain and I like to see my own picture. I like to hear myself talk. But number two, I'd like these things to be more human. I like to make you're not just listening to a recording. There's a real human being really trying to talk to you, really trying to explain this stuff. What does the research say? The research says that my face is causing a problem here. So sometimes we as teachers tend to ignore the research, even when we know what's good for students. What should you do? Well, I'm going to leave it to you with this. Here's another image, just by the way. We were working with remote control telescopes looking at galaxies. You can see the different astronomers. Dave McKinnon is down here in the right-hand corner. He's in Australia. Scott Mecca is there. He was in Sheridan, Wyoming. I think I happened to be sitting in a dark room in Florida at the time. But does that help or not help? We tend to think that having the pictures there helps, but statistically, research project after research project shows it doesn't. Couple more interesting things. For example, here's a short video clip of not a human being, but a mechanical human being. The research question here is, I've got a mechanical voice compared to a real person. Do students learn better from a real person, or do they learn better from a mechanical voice? Turns out that students learn better from a human being voice rather than a mechanical voice. This is why industries like airline industries and insurance companies spend so much money on their voice systems, where they're saying, hey, push 1 if you're interested in talking about insurance, push 2 if you'd like new siding on your house. So if you want students to learn, then we probably shouldn't be using mechanical voices. But is that always true? All right, so there's a mechanical voice, and that's a pretty important mechanical voice. Should students be exposed to learning from Stephen Hawking's ideas from this mechanical voice? Turns out we can do that experiment too. We can have Stephen Hawking talking for 40 minutes with his mechanical voice, or we can have somebody with a more natural human voice read that transcript, and we can test students. Do they learn better from the real thing, or do they learn better from the human voice? In this particular case, again, students learn better from a voice that's familiar to them. Now, does that mean you shouldn't use Stephen Hawking's voice? Well, absolutely not. This is a culturally important thing in science education. But if you were to watch this TED Talk, you'd see what would happen is you'd listen to Stephen Hawking talk for about a minute, and then his voice would fade away, and a human voice would continue on reading his transcript. And that's how we manage these sorts of things. But you can imagine the questions you could ask is, what about a male voice to a female voice? Does it matter if the students are male students or female students? What about a heavily accented Southern American voice versus a more crisp, appropriate Pakistani voice using imperial English? Those studies still haven't been done in the context of science, though they've been done in a lot of other areas, and the results are mixed. If we're really interested in understanding how do we help students best learn science, particularly if they're going to be learning science on computer desktops more and more frequently, these are really, really interesting questions. All right, we're almost out of time here. But in general, what we discover is whether we're looking at extraneous processing issues, essential processing issues, or generative processing issues, the more stuff that students get fed, the more things that are unfamiliar to them, the less they're going to learn. And that's because the brain only can take in so much information at a time. We usually call this cognitive overload. And even when you're reading web pages and there's a change in font size or a change in color background, all those sorts of things lead to extra extraneous information, which distracts students' ability to learn the material. In the context of thinking about astronomy textbooks, I often have professors that'll tell me, oh, I'm not going to use an astronomy textbook because all that information is free on the web. I got this website over here to talk about Mars, this website over here to talk about Saturn, this website up here to talk about black holes. Well, if they're not all written in the same voice, they're not all written in the same font, they're not all using the same page layout, that's additional information that students unnecessarily have to process, which negatively impacts their ability to learn. And we know this for testing. So, for example, does the room you take your test in matter? We've done the experiment many times where you take a group of students, half of them have to leave the room for the final exam and go take their final exam in a room different than they learned in, and compared it to the students who got to stay in the classroom, the physical classroom where they learned the material. Turns out if you get to stay in the physical classroom where you learned the material, you do better than when you take a final exam in an unfamiliar environment. Now, there's all kinds of theoretical reasons we could push for that. You know, do students remember, okay, when somebody wrote F equals MA on the board, he wrote it over here on the board, or when she was doing the dissection, she was standing right here, and I remember her standing here, so I remember that's what the dissection looked like. Or is it just being in a new room is too noisy? Wide variety of possibilities there. That research has been done in a number of different areas, but not so much in science education. So what I wanted to do was just to give you a bit of a sense of what some research is being done in cognitive science that's not really gotten very far into science education. And these kinds of things could make really interesting research projects or class projects for those of you who are doing qualitative instruction, those of you doing quantitative instruction. These different classes, you're looking for projects, there's a lot of really good juicy ones right here.